All right, we are continuing with forces, and today we're going to be looking at some details regarding Newton's laws of motion. We're going to look at angled forces and how to deal with and work with those, and then also, hopefully, we'll get into some systems of objects. All right, so let's get right into it. You should already have Newton's three laws written down. We went over that in the last video, and we went over some things about them, but we're going to get into more detail, specifically with the second and third law, that's going to help us to be able to solve some problems with them. All right, so there's not too much we're going to say here about the first law. I mean, knowing how the first law of motion would apply to a situation is important. Knowing that, hey, this object is at rest, so it's going to stay at rest, or this object's moving at constant velocity, so it's going to stay at constant velocity until acted on by an unbalanced outside force. So the main thing we're going to say here is that the first law is also known as the law of inertia. So we also call this, it's also called the law of inertia. So we're going to talk about inertia, what that means, why do we call this the law of inertia? Because it's the first law is really based on this concept that objects, because it's based on objects tending to maintain their state of motion. And what we mean by that, maintain their state of motion, is if they are moving at a constant velocity, they will tend to maintain that state of motion. If they are stopped and at rest, they will tend to maintain that state of motion as well. And if they are accelerating, if the current state of their motion is that they're accelerating, that's because there's an unbalanced force acting on them. And if that unbalanced force continues to act on them, then they'll continue maintaining that state of motion. So even when the state of motion changes, an object goes from being at rest and then unbalanced force acts on it, so it moves, or it's moving at constant velocity, unbalanced force comes along, so it accelerates, slows down, or speeds up. And even when that happens, when we accelerate, so the state of motion changes, if that unbalanced force maintains, you keep pushing an object. If it depends on the other forces acting on the object, but if you push an object and you provide an unbalanced force and you keep providing that unbalanced force, it will keep accelerating. This is like if you could push down your gas pedal more and more and more and more to keep providing more force, you would accelerate, well, until you reach the maximum velocity your car can get to. Okay, so let's talk about inertia. Now that we've mentioned objects will tend to maintain their state of motion. All right, so inertia is defined as the following. Inertia is an object's resistance to changes in its motion based on its mass. All right, let's break this down and talk about it. So, what this means is that every object has resistance to changes in its motion. If something is sitting still, it's going to resist any attempts to move it and have it stop sitting still. This is a little different than the static friction we mentioned before. Static friction also resists changes in an object's motion, but even if an object were sitting on a frictionless surface, there would still be some natural resistance to changes in the motion of the object based on its mass. So let's talk about this. If you had a 1 kilogram object, pretty small, like it's not a huge amount of mass. If you had 1 kilogram sitting on the ground, and then you had 10,000 kilograms sitting on the ground, and you push on them both with 1 Newton of force. They're both going to accelerate. In fact, even the one with a huge 10,000 kilogram mass will in fact accelerate. But the equation, we're going to sort of jump ahead a little bit here to the second law. The equation that really shows us this is Newton's second law. So let's write that up here because we're about to get into it anyways. So it says the sum of forces is equal to mass times acceleration. So let's just put in some values here in our heads and work with this. So if mass was 1 kilogram and your force was 1 Newton, well, the math would be pretty easy. Your acceleration would be 1 divided by 1, and you get 1 meter per second squared of acceleration. So if you take a 1 kilogram object and put 1 Newton of force on it, on a frictionless surface with no other forces resisting it, so it's just applied force providing that acceleration, then your acceleration is 1 meter per second squared. If your mass is 10,000 newtons, or sorry, kilograms, if your mass is 10,000 kilograms and you put 1 Newton of force on it, yes, there would technically be an acceleration, but the amount of acceleration to solve for A would be 1 Newton of force divided by 10,000 kilograms of mass. So you'd get like 0.00001, however many zeros there are there. So a very small acceleration. So even though a huge, huge object would accelerate without any friction, if there was truly no friction, even when it experiences a tiny force, that acceleration depends on the mass and the force. If you put a huge force on a tiny object, it'll accelerate a bunch. If you put a really small force on a really massive object, it's not going to accelerate very much at all. So the mass, along with the amount of force that determines acceleration, right? It does depend how hard are you trying to change the motion of the object? How hard are you pushing or pulling? But objects will resist those changes in their motion. So big objects with lots of mass are not going to accelerate as much because they have more inertia. They resist these changes in their motion to speed them up or slow them down. And you require a lot more force to significantly accelerate an object when it has a bunch of mass. That's the idea of inertia. And that's what the first law gets at. If something's sitting still, it'll keep sitting still. If it's constant velocity, it'll keep going at constant velocity. And then when you put um, an unbalanced force on it, going right into Newton's second law, we can start looking at how inertia really shows up mathematically and affects things. Okay, but inertia is just this concept that shows up conceptually in the first law. Where we actually use inertia and mass and with force and acceleration is the second law. So let's go through that. This is going to be one of our super duper frequently used equations, like very frequently used. This is one of the core equations for Unit 2. I would argue where the big five equations took a role in Unit 1, this takes a similar role in Unit 2. Like, we're going to be summing forces a lot. Now, within that will be things like finding the force of friction, finding gravity, force of gravity, etc. But summing forces and using sum of forces equal to mass times acceleration is a big, big thing. Okay, so what are we going to do with this? Well, as I kind of just mentioned, we will be, so this is, of course, the second law. We will be summing forces with this equation. All right. What that's going to do then, which tells us the total or net force. We talked a little bit about net force. That phrase just means after we've accounted for all of the forces acting on the object in total, after we could factor in like one force pushes to the right with 10 newtons and another force pushes back to the left with -5 newtons, and they in part they counter each other or cancel each other out. But after all that's been accounted for, what is the total result or the net force. So telling us the total or net force acting on an object. Okay, so using this sum of forces, so using sum of forces and the mass, m, we can also find or solve with the acceleration of the object. So in our equation, the three things are force, mass, and acceleration. We already talked a little bit earlier about how the direction of force and acceleration will always be the same as each other. That's a really interesting piece of Newton's second law, is whatever direction your net force acts, if the forces all add up together or work with each other or against each other and your result is a net force to the right, then your object will accelerate to the right. So force and acceleration always have the same direction in Newton's second law. Okay, so we can solve for acceleration. If we were given an acceleration, we could solve for something else, like we could find the mass if we knew the net force and the acceleration. So just our algebra allows us to solve for any of those things. In fact, um, yeah, we'll talk a little bit about equilibrium in a bit, and that's one of our interesting tools often to solve for individual types of forces. But yeah, that's the other thing too, is this is kind of the answer to the lack of equations earlier on. Like tension doesn't have an equation, applied force doesn't have an equation. Um, what else? Drag force doesn't have an equation. Normal force doesn't have an equation. There's lots of places where we're going to use this, Newton's second law, the sum of forces, to be able to find something like tension or normal force where we wouldn't normally just be able to find it from its own force equation. Okay, cool. So let's talk an important thing about vectors. So there's a really important piece here. So importantly, because force and acceleration are vectors, we must make sure to use separate x and y equations for Newton's second law. When we are dealing with horizontal versus vertical forces and acceleration. So that basically means we actually end up with um, two versions of this, and we could tell from our vectors, it's pretty easy to put an x subscript on the force and the acceleration. Now you have an x horizontal version of Newton's second law. If you're dealing with vertical forces acting up and down, causing acceleration vertically, just put a y subscript on forces in the y direction or acceleration in the y direction. Mass doesn't need a subscript because it's a scalar like time. We never had to subscript time with kinematics. But we did have to subscript Vx initial, Vy initial, acceleration x, acceleration y, delta x, and delta y. Similarly, we need to make sure we're looking at vertical forces with vertical acceleration or horizontal forces with horizontal acceleration. All right, this second law also ties to the idea of equilibrium. Okay, so what is equilibrium? Well, let's define it. So when all the forces acting on an object or system, which we'll look at later, add up to zero, meaning that the sum or the net force is zero. We call this equilibrium. By far, the most common example of equilibrium is gravity and normal force. For every single object that you see sitting on your table or floor or bed, if it's not moving, that means that gravity pulls down on that object and the normal force from the surface pushes up on that object, and they exactly balance each other out. So equilibrium is most commonly seen through gravity and normal force balancing out. Um, so there are three, we can specify three types of equilibrium. Let's put them here. So we'll get to the vertical one in a second, which we just referenced with gravity and normal force is a common vertical equilibrium. So horizontal equilibrium this would mean that all the horizontal forces sum up to zero. And when that's the case, this means that the object or it could be a system. So sometimes we'll run into like a system of objects where that's relevant. Oop. What's going on here? There we go. And the object has zero acceleration in the x direction. Now we are not done with the differences between acceleration and velocity because people will continue to mess these up from time to time. This does not mean your object is stopped. People will assume, oh, so all my forces balance out, they add up to zero. My object has zero acceleration in the x direction. Surely it must be stopped. That doesn't mean it has to be at rest. It could be. That is one option for having zero acceleration is it could be at rest. But the other option is it could be moving. It has velocity, but that velocity remains constant, right? That's also zero acceleration. If your velocity stays at whatever value it's at, constant velocity motion means zero acceleration. It's not speeding up, it's not slowing down, but it is moving. Okay, so equilibrium is all your forces balance out in the x direction and you have no acceleration in that direction. All right, let's look at vertical equilibrium. As we might guess, it sounds pretty similar. Vertical equilibrium means all the vertical forces sum up to zero. Common example is gravity and normal force, but could be others, could be other vertical forces. Whatever they are, all the vertical forces sum up to zero. And the object has zero acceleration in the y direction. An example of this actually is, besides gravity and normal force balancing out, is like skydiving with drag force, because the force of gravity always pulls down on us. But if you go skydiving and you reach terminal velocity, what that means is you stop speeding up in the vertical direction because the amount of drag force upwards has actually balanced the force of gravity. So there's no net force. All the forces, gravity downwards and drag force upwards, add up to zero, and you don't end up speeding up anymore. You have zero acceleration in the y direction. So you don't fall faster. You keep falling at terminal velocity. You still move, but you have no more acceleration. So that would be an example of vertical equilibrium while an object or person moves, whereas something sitting on your desk is vertical equilibrium where the object remains at rest because gravity and normal force just add up to zero. Total equilibrium, one more piece here. Put that in here. Total equilibrium. This means that all forces in all directions so all forces in all directions sum up to zero. And, or I should say, sum up to zero net force. The object has zero acceleration in any direction. Okay. And that's equilibrium. So equilibrium is just when your forces either horizontally or vertically or both horizontally and vertically add up to zero. So you either get horizontal equilibrium, vertical equilibrium, or total equilibrium. Okay. Now, let's move on to Newton's third law. So, second law, forces sum up to result in some acceleration. When you sum up all the forces up here, you say, okay, let's add them all up in the equation, sum them all up. Positive forces go in with a plus sign. Negative forces going the other way go with a negative sign. So you'd have like 10 newtons minus 7 newtons plus 4 newtons. And do all your math, sum up your forces, find what the total or net force is, then set it equal to mass times acceleration. And we can look at all kinds of things with this, like an object or system that has more mass will accelerate less when experiencing the same force as something with less mass. And so there's all kinds of ways we can look at the resulting accelerations of things, and we'll be able to dig into the particular forces. We can use equilibrium to say, hey, if these add up to zero, that's actually going to be a helpful tool for us to solve for those forces. Because if we know gravity is 20 newtons downwards and the object is in equilibrium, well, then the normal force had better be 20 newtons upwards because it's supposed to balance out gravity. So it can actually, equilibrium can actually tell us what some of these forces are that we might not have otherwise been able to find. So it's actually a really, really useful tool, along with just Newton's second law in general. Very handy. Going to see a lot of use out of that. All right, third law. Let's talk a bit about this. So the third law, again, you should have it written down. We're not going to write it out in its entirety. Third law is most often seen in a particular type of problem. And that particular type of problem is called, unsurprisingly, a Newton's third law problem. So probably no surprises there. So in AP, what's going to happen is this problem is going to involve. So this problem is involving. Quote, third law pairs of objects. And a third law pair of objects is one that, well, satisfies Newton's third law. So let's remind ourselves of what that is. So in order for objects to be a pair in this way, there must be, first of all, there must be exactly two objects and those objects must be exerting forces on each other. So must be exactly two objects exerting forces on each other. That are equal in magnitude and opposite in direction. So if AP gives you a problem and they say, are these two forces a third law pair? They won't say it as explicitly as that. So they might say, here's a scenario. Here's some forces that are going on. Here's some objects that are involved. And they might ask you, like, how big is this one particular force that this object is experiencing? And what's going to happen with that is you're going to have to look at the scenario and say, all right, in this situation that I'm presented with, do I have exactly two objects that are exerting forces on each other? If you can pick out a pair and say, okay, I've identified this pair of objects that is exerting forces on each other, and those forces are equal in magnitude but opposite in direction, then you have a third law pair. Common examples would be gravity. Once we get into, like, we'll get to universal gravitation, where we look at the Earth and the moon, or a planet and a satellite pulling on each other. Even if you have, you can take this to a smaller scale. Even if you have like a car and the Earth, both of those objects put forces on each other. So Newton's third law says when the Earth pulls on the car with a force of gravity equal to whatever, some amount of newtons, The car pulls back on the earth with an equal force but opposite in direction. If you know, they'll have like a brother and sister that are skating on the ice or something, and if the brother pushes the sister or the sister pushes the brother, the other will push back on them, and that's not even like retaliation. It's not like if you push me, I'll push you. It's like literally if you push on someone, you will immediately experience a force that is opposite in direction but equal in magnitude. So if you're both on ice and you push off someone or push them, you're both going to start accelerating. So that's uh that's just the basic understanding of Newton's third law that we're working with. So now these can be tricky. So one way they'll be tricky, and we'll call them out on their sneakiness. These can be tricky um, because um, gravity and normal force, for example, Fg and Fn are not a third law pair. We might be like, whoa, hold on, what's going on? That seems like a third law pair. Um, third law pair. Let's explain why they're not. Okay, so I'm going to draw a little table or something, and on that table is a box. So we've got object-wise, the box is an object, the table is an object, and the Earth is an object. A very big object, but we're going to treat the Earth as just an object. So the forces that are happening here, sure, we have gravity pulling down with, let's say, 5 newtons of force, and the table supports it and pushes back up with 5 newtons of force. So we might think, well, aren't these just equal in magnitude, opposite in direction? Shouldn't this be a third law pair? What's happening here is we have 3, not 2, objects that are putting forces on each other. So the 3 objects are the table, the box, and the Earth. Gravity, which is one of those forces that we might think, oh, surely gravity and normal force are a third law pair. One of those two forces, gravity, is the Earth pulling on the box. If you were looking for a third law pair, it would have to be Earth pulls on box, box pulls back on Earth. That mutual force of gravity between them would be a third law pair. But that's not gravity and normal force. Normal force is the table pushing on the box. So gravity is Earth pulls on box. Normal force is table pushes on box. Those are 3 separate objects: Earth, box, and table. And and both of on the receiving end of both of those forces is the box. So these cannot be a third law pair because both gravity and normal force are acting on the box itself. Instead, a third law pair needs to be object 1 acts onto object 2, pushing or pulling it. Object 2 acts with a force back onto object 1, pushing or pulling that in response. So this is a classic one that you don't want to fall for, where AP might try to make you think that gravity and normal force are a third law pair. So we really just want to make sure for the forces that are happening here, do we have 2 objects exerting forces on each other, pushing or pulling on each other, and those forces that will then be equal in magnitude, opposite in direction. Because that's what the third law says is if you have an object 1 pushing or pulling on object 2, there will be a force acting back in the opposite direction from object 2. Okay, we'll see some of those examples. We'll go through some of those types of problems. All right, we're going to swap over to angled forces. So, see what we've got here. So for angled forces, the summary here is that similar to initial velocity from projectile motion, So just like when we had projectiles and we had initial velocity that was at an angle, many forces, or at least some forces, I don't know about a ton of them, but I'd say a good amount of forces. We could probably get away with saying many forces will act not only in the x or y direction, or we'll say, I'm losing my ability to write. Come on now. Oop. Oh, okay. It decided sometimes it just be doing things. Many forces act not only, or not um, only in the x or y direction, but instead at an angle. We're going to look at those in just a second. We'll kind of break them down and see what we can do with them. All right. When this is the case, we use our knowledge of vectors in trigonometry to find the components of those forces. Okay. And not only that, not only will we find the components of those components, which will then be used in appropriate x and y versions of Newton's second law. Okay, great. So I, I guess I should actually specify here of Newton's second law equation. So this equation for Newton's second law, which we have looked at just a little bit ago, allows us to do things like find acceleration. We can find a specific force using Newton's second law. We're just going to be using that a bunch. Okay. Cool. So this summarizes what we're going to do with angled forces. So similar to the starting velocity of projectile motion, when forces act at an angle, we're going to use vectors and trigonometry knowledge along with sine and cosine to be able to find the components of those forces that are used in appropriate x and y versions of Newton's second law equation. Great. Let's start setting this up. One more reminder before we do is for free body diagrams, we're going to go ahead and abbreviate that FBD for free body diagrams. AP wants us to draw the entire angled force on the diagram. the entire angled force on the diagram not its components. We do not want to draw force components on a free body diagram. Now, I take issue with this. I think drawing components is actually very helpful, but AP does not like to do it. Okay, that's all right. We'll go along with their little rules and whatnot. Okay, so let's draw an angled force. I'm going to do sort of a scenario. We'll put the ground here, and there's a box or an object of some kind. And we're going to put a force on it. So we're going to act like so. Actually, let me get my perfectly straight lines out and put those in here. Drag it over here. Something like that. See if I can get the right angle. Let's see, what should I shoot for? Let's go for like a 35-degree angle, something in that ballpark. Hopefully that's good. We're going to throw in some other things here. Oops. Got to remember how to change the color of my line here. All right. So I'm going to do some blue components as well. So we learned that any vector, including velocity, including force, acceleration, whatever it is, any vector that is acting at an angle has components. So we're going to put those components in here. And then we're going to look at how to find them. All right, let me draw some little arrows on here to show the direction of forces. So, oops, for that guy. All right, so there's that. And then do this and that. All right, let's identify some forces. We'll draw an angle. Oh no. Well, apparently I've hit my limit. It's telling me I have to delete components. That's all right. We'll have to redraw this, but that's okay. We'll do it. Okay, we're going to add a new page. We're learning, we're evolving. All right, so let's do that angled force on here. In fact, while I'm at it, I'm going to draw the ground as a flat line. Everything can be flat. Okay, there's that. Let's throw our object in. I'll actually draw that. Object. Boom, boom, boom. Okay. Here's my force. I'm going to pick an angle to act. Again, we're going for about 35, give or take. Another line. And you'll notice as we draw components of forces, we are just making right triangles because components of vectors always form right triangles when you have an angled vector and then you draw its two components, you will get a right triangle. I'm going to have to move this out a little bit. A right triangle is not a right triangle. Let's see if I can get it to go. Come on now. I just want you to go straight up and down. I don't know why it's struggling so much to do so. I believe. Come on. All right, surely this time. Actually, call it good enough here. All right, well, I am sad by the fact that it is there. That's close enough. Okay. Let's draw some arrows so we know what direction our force is acting. There we go. I'm even going to put an angle in here. Let's do 30 degrees. Let's do 35. I think that's more reasonable based on how I drew it. There's our nice 35-degree angle. And this is our force. Let's say it's an applied force. Here's your person or animal or whatever pushing or pulling on the object. And we're going to keep it general for the moment. Then we'll get into specifics of the 35-degree angle, etc. Okay, so there's our applied force. We'll fill in more in a little bit. I'm also going to draw some components on that force. And in fact, I've already drawn them. I'm just going to add some arrows onto the tips of these. Boom, boom. There's that and that. So this is F A Y. This is F A X. So all we're doing, very similar to what we did in Unit 1, is we're adding X and Y subscripts onto our angled vector components so we can be clear about, all right, this person is pushing or pulling at an angle of 35 degrees, and they're pulling, let's say they're pulling up and to the right. But the two components of this force are getting at the idea of how hard is this person pulling to the right and how hard are they pulling upwards? Because sure, we could know that it's 20 newtons of force, the black arrow or the hypotenuse at an angle of 35 degrees, but how much force exactly are they pulling with to the right, and how much force exactly are they pulling with upwards? That's what our vector components tell us, right? Which is very useful information when we're going to be summing forces in the x and y direction. So just like we did with projectile motion, we split apart the angled force into its components before doing things like our big five equations back in Unit 1 and doing our Newton's second law sum of forces here in Unit 2. Okay, so let's break down how to do this. Hopefully it feels pretty comfortable or familiar because we actually did a very, very similar thing back in Unit 1. So we're first off going to look at this x component. So using the cosine of the angle theta as equal to adjacent over hypotenuse. So the adjacent side to our angle theta is FAX over the hypotenuse, which is the total applied force FA. What we're going to get from that is we're just going to multiply both sides of our equation by the applied force FA. That is your hypotenuse of the right triangle, the total applied force. And then what we get is FAX is left by itself, isolated, equal to cosine theta times FA. Now, this is a good spot to note. This doesn't have to be applied force. It could be any type of force. Applied force is just a common one because normal force we pretty much never have at an angle. Even in fact, even when we do have normal force acting at an angle on a ramp later on, we'll make it so that it's not at an angle. Um, but yeah, it could be any force. It could be tension acting at an angle. We'll even get to gravity, where gravity acts at an angle. So this could be any type of force. So the more generalized expression for this would be the x component of some force is equal to cosine of theta times the total force itself. Now, this is a good equation to use, and it's a pretty commonly used one. The only word of warning is we should say check if that x component is adjacent to the angle theta. Because if it is, which in this scenario, FAX is adjacent to the angle, so yeah, cosine theta times the hypotenuse gives us that x component. There might be a scenario in a couple of problems based on how they set up your angle where this might not be the case. This is like our default. We typically tend to do this. And in almost every case that we encounter, this will be true. But you just want to check and make sure if I'm using cosine, I better make sure that this component, fx, is in fact adjacent to the angle theta. If it were opposite, we'd have to use sine. And speaking of sine, that's what we typically use for the y direction. So let's look at that here. In fact, there'll be a specific use case for ramps. On a ramp, we're just going to switch it, and we're going to use cosine for y and sine for f when it comes to cosine for y and sine for x when it comes to gravity. But that's a whole nother story for later. So using sine theta equal to, in this case, fay over fa, we can set up the same thing where we would multiply both sides. By the applied force, giving us fay equal to sine theta. Oops. Got a rogue drawing here. There we go. Sometimes my Canva just goes rogue on me. All right. Sine theta times FA. Now we can also generalize this equation. That's probably a good idea because we don't want to assume that applied force is the only force we can split into components using an angle. So instead we'll say more generally, the y component of an angled force is typically found by sine theta times the total force itself, or the hypotenuse. So we still want to check, in this case, if that y component is opposite to our angle theta. So just be on your toes with that. Don't assume that always you use sine for y and cosine for x. Yes, a large amount of the time that is the case, but we just want to keep our eyes open for which angle are we actually given, which one are we dealing with, and for those components of the force, of the angled force, is the horizontal or vertical component adjacent or opposite to the angle. Okay, now I'm not going to actually fully solve this one. I chose the 35-degree angle, but I'm not going to go through. And you could test this by choosing like 10 newtons or 20 newtons and give it a shot and see what you get there. But we're going to leave it there for now as some general notes. Okay, let's talk about systems of objects. I don't think we're going to trying to evaluate, because systems of objects does take a while. We'll try and get through center of mass. I think we can get through center of mass. So let's make that the goal today. All right. So systems of objects and center of mass. The basic idea behind systems of objects is pretty simple. And honestly, the basic idea behind center of mass is pretty simple as well. How we use them in the details of solving problems with systems of objects gets a little tricky. Center of mass, once you understand the equation, is actually really not too bad at all. So a system of objects is defined as Uh, Two or more objects that are generally we could say like connected together in some way, where we have the option to consider forces acting on individual objects or on the system as a whole. Now, later on, I'm going to call back to things like the human body itself is actually a system, like your heart or your liver or your bicep muscle. These are things you could consider as a separate object, but your body is, of course, very interconnected. The interactions between not just forces but electrical signals and body processes that happen between all the parts of your body are really important. So your body is a system of objects, and what we could do is we could look at just your heart, and I'm sure a doctor would agree that for certain issues that people might be having, you want to look at like, well, if you're having heart issues, then you just want to look at the heart, like what things are affecting that particular organ, like what forces are acting on that, versus you could also consider your body as a whole. So that's one kind of image. Another would be like a car with passengers, and maybe there's a bag of groceries in the back seat, and there's a dog in the back seat. So you could look at what forces are acting on the dog right now, or what forces are acting on the bag of groceries, or you could just consider the car as one whole thing and say, hey, all these objects or parts that make up the system, let's just treat them all as one combined. We could call it the car, which would then include everything inside of it. Even the car itself has lots of parts, right? The wheels, the engine, the steering apparatus, everything that makes up your car could be considered an object by itself. So really everything we deal with is a system of objects. It's just how individual do we want to go, right? Do we want to be able to, well, let's go ahead and analyze the forces on the driver of the car and let's look at that versus let's just treat the car as one single combined object. That's the idea behind a system is, and we're not going to get super complicated with this. We're not going to be doing like too much with like vehicles and a bunch of stuff inside them and all that. We'll have pretty fairly simple systems where we've got a couple, like two, maybe three objects, and they're connected in some way. And what we'll be able to do is we'll be able to look at, well, we could consider the forces acting on one individual object, or we could treat all these objects together as one combined object or system. And that entire system we could look at the forces acting on it or what's going on with it. Okay, so that's the basic idea of system of objects. And we'll get more into some specifics on systems later on. Probably in the next video, we'll get into some more details, but let's talk a bit about center of mass. So center of mass, which we can abbreviate COM if you'd like. Center of mass becomes relevant for systems. It does relate heavily to systems. But can also be related to where the force of gravity acts. This is going to come up later on in Unit 5. When we talk about torque and rotation, we'll come back to like center of mass as the location where the force of gravity is acting. For now, it's not super important. In most cases that we specify exactly where we're going to draw or treat the force of gravity as acting, but yeah, and technically gravity acts on all parts of an object or system, but there will be an especially important piece with this when it comes to calculating things like torque in Unit 5. Okay, so what is center of mass? It is simply the point or location where the mass is distributed evenly on either side of that point. Or we could add in here or like above below. So if you want to find the center of mass like vertically or horizontally, we have ways to do that. We'll write those equations in just a little bit. So one thing to note here is we won't find this for single objects. So if you just have a box sitting on the ground or a bicycle on the street, we're not going to really worry about finding center of mass for a thing that we're considering as one single object. But we will come back to this in Unit 5. When we look at a single object with a center of mass and where the force of gravity acts for that object based on the center of mass when it comes to finding torques. And it turns out, so for single objects, we're not going to worry about calculating the center of mass of a bowling pin or something like that. But for systems, when we have multiple objects together and we're looking at a system, for systems, we have an equation to calculate the center of mass. And we also have a way to find its velocity. All right, let me just make sure I pull up the right equation here because I don't want to lead you astray with the wrong one. This is an equation they had not added to the equation sheet, so you're probably seeing me be not super familiar with it because, well, it wasn't on the equation sheet for a long time. For many years, it didn't show up on there. So we have a way to calculate the center of mass and its velocity. We'll talk a little bit about this, like what do we mean by the velocity of the center of mass? So we'll draw that out here. All right, the equation itself looks like this. And x center of mass, this is the symbol that AP uses for the center of mass is an X subscript CM, standing for center of mass. So X center of mass equal to the sum of all the individual masses. So they write it like this: MI XI divided by sum MI. Now, hopefully we'll do some examples, and like AP has some good examples of this. We could also write it for the Y direction. So just like the X, we could say our vertical center of mass is equal to the sum of each individual mass times its Y location or position divided by the sum of all the masses. All right, so what do all these symbols mean? Well, on the numerator, we're just summing up each individual mass times its X or Y location. We'll do some of this more in class, but I'll give a brief example here. So if you had a location of 0, and I've got object 1 here, object 2 over there, and they're like connected. Maybe I've got a rod or a wire going through them. I would take this mass, M1, and this mass, M2, and let's say this is 1 meter here, and then 2 more meters out to here. Well, in this equation, what I would do is I'd say the X center of mass is equal to, and then I'm just going to sum them up. So what it means by MIXI is you take the first one, which would be M1 in this case. Here's our first little mass here. And we say, all right, there's the mass M1. Where is it located? What is its position or location relative to 0? And we say, okay, well, the first one, mass 1, is located 1 meter to the right of 0. Okay, so we do mass 1 times 1 meter. Great. Then we're going to add on to that, and we're going to just sum up. We're doing a sum here, so we're going to sum up. What about the next mass? Okay, well, that was M1. Next mass is M2. Okay, so M2 is located 3 meters to the right of 0. 1 meter here, then 2 more there. So we're going to take M2 times its location of 3 meters. And if we had more, we could add on. We could do M3, M4, M5. We could add up any amount of masses and their respective locations. And then we divide by the sum of the masses themselves. So we would do like M1 plus M2. And if we knew the amounts, so maybe the problem told us M1 is 4 kilograms and M2 is 6 kilograms, we could plug in numbers and we could solve exactly for the center of mass. So that's what the equation looks like, is just go object by object, take the mass 1 first and mass 2 and mass 3, however many objects you have, and for this system of objects, just go one by one and say, all right, the first object, where is it located? All right, it's this many meters away. Cool. Add on to that the next object. Where is it located? How many meters away from 0? Okay, now the next one. And you add up or sum up all of the objects times their locations, and then simply divide by the sum of all the masses. You can do this in the Y direction too. If you've got a distribution of objects at different heights or different vertical positions, do the exact same thing. And so this one tells you where exactly is the location where the mass is distributed evenly on either side of that point. And also, you could think of that as like center of mass is also a balance point. If I were to pick up this object and like put my finger on, if there's a rod with 2 objects attached to it, if I were to hold that rod at a particular point where I want it to balance, the center of mass would actually allow for that balance point to occur. All right, one last equation we're going to mention, which is, I think it's near the bottom of this. Well, actually, I should adjust this, do a little erasing. In fact, I think I might have this. Let's see. Why can I suddenly not find the eraser? There it is. Because the equation that's on the sheet, I misspoke with velocity. It's actually acceleration. So it allows us to find what is the acceleration of the center of mass. All right, so what does this look like? Well, let's box up our equations so they look all nice and cool. There's that one. There's that one. Now, the only one that's actually on your equation sheet is the x version, unsurprisingly, because all of our x and y things, we just have x versions of them. Um, yeah, so uh, the acceleration of a system. And it's funny because this is the way that they write Newton's second law. On the sheet, Newton's second law is not written just as sum of forces equals mass times acceleration. It's actually written in terms of systems, which is fine because technically, even an object by itself could be considered a system. Usually, we'd just say there's two or more objects in a system. We would just take one object by itself to be just an object. But you could say it's not wrong to say that there's a system that consists of only one object. So whether it's a system that it's experiencing forces, multiple objects at once experiencing forces, or whether it's just one object by itself, we can use this equation, which is really just Newton's second law. So acceleration of a system is equal to the sum of all forces acting on that system divided by the mass of the system itself. So they write Newton's second law a little bit weirdly here, but that's fine. They just divided the mass over to the other side. And they also have it written as, well, that's just the net force, force net, divided by the mass of your system. So we'll do more with systems. We'll look at we'll be able to look at individual objects within the systems to use Newton's second law and sum of forces, or we can find the center of mass of the system. And the acceleration of the center of mass of the system is this. So for a system, the acceleration of the center of mass is just using Newton's second law, net force divided by the mass. Okay. Those are a couple equations, one of which is really just Newton's second law, that are centered around systems or center of mass. Okay, one more thing we're going to say before we wrap this up is we're going to talk about a phrase that's connected to this acceleration piece. So what happens is when we're solving problems involving center of mass, we may hear the phrase or see the phrase quote, acceleration or velocity of the center of mass of a system. Okay, so what does this mean? When a problem says find the acceleration of the center of mass or find the velocity of the center of mass, this just means if we were to treat oh no, come on, come back to me. I've lost my ability to draw. I really think it is as you get to the end of these whiteboards. This design is approaching the limit of drawing strokes. Wow. Hearts, shapes, and sticky notes. It really does be going crazy towards the end. All right. We'll see if we can make it. If we were to treat the whole system as one single object what would the acceleration or velocity of that object be? So the easiest way to find the acceleration of the center of mass is just with the equation we have. Um, or what we can do is we can simply ask, does the location of the center of mass change throughout the process that's happening? Because if your location of the center of mass changes, and we'll do there's some problems. It's probably easiest just to look at AP problems with this because I could try to like explain and do an example of it, but really there's a few problems where you just have to find the center of mass of a system and then look at like, does that particular location where the center of mass is, does that change? If it does, then the center of mass of your system has some velocity to it. And the acceleration of center of mass of the system is easy to find with the equation for our system, with the net force and the mass. But um, yeah, we'll talk more about this later on because it's a little harder to like fully draw or explain. But if you ever see something in a problem that says find the acceleration or find the velocity of the center of mass, all that means is just treat the whole system as a single object, and what would the acceleration or velocity of that object be? Okay, we will come back to systems. We'll talk about internal, external forces. We'll talk about examples of systems and the forces within them, the forces acting on each other between those objects in the system. We will do Atwood's machines. Atwood's machines are a very specific type of system of objects. So, yeah, plenty of stuff to do with systems. But for now, we're going to call it on the video. So, definitely make use of the Padlet. We have that Padlet for asking questions. We're really starting to get into the main part of forces where we're using Newton's laws and looking at specific things like what if you have an angled force when it comes to the sum of forces for Newton's second law, and how do we do that in the x and y direction with those components? Systems are a big category of scenarios in which forces are acting, and we have to look at systems. So, yeah, definitely ask whatever questions you have on that Padlet anonymously on Schoology right below or below our daily agenda, or bring your questions to class. All right. Thanks for watching. We'll see you in class, and we'll be solving some problems with forces, Newton's laws, and systems.